I was about to introduce myself. My name is Radek Sikorski and I am Technical Support Manager at the Export Department of SMI company. SMI is a family company from Poland that has made the protection of human life its mission. We are ventilation and fire ventilation manufacturer, and for more than 12 years now we have been active in the field of pressurization systems, creating state-of-the-art technologies. So we are building higher and higher, and that's a fact. There are 200 buildings worldwide that are higher than 250 meters, and quarter of them were built in last 10 years. As their number increases, so does the risk of fire. At the same time, the taller the building is, the more people work or live in it. Keeping them safe is at the core of modern building design. At the same time, there is still a very popular thinking, of course not here, but we meet this opinion very, very often, so do you, I am sure, that if something is very simple, very basic and not advanced at all, it has to be reliable. But is it though? For example, in the automotive industry, it is obvious that if car has power steering, traction control system, ABS, and computer to have the knowledge about the current state, technical state of a vehicle, it provides greater safety. We are even trying to implement self-driving cars to avoid human mistakes. Cars without all of those systems are also drivable, but mainly under easy conditions, on wide, dry, straight roads. But I can assure you that the fire situation is the most demanding curvy road you could possibly imagine. So we have smart cars, we have smart phones, we have smart buildings, smart cities. It is time for smart fire protection as well. I would like you to keep in mind the scale, because when you choose the modern car, you protect few people, but when you choose modern, smart fire protection system, you are investing in protection of hundreds. And why is it so important? Perhaps you know what is the main reason of deaths during fire. Not flames, not burns, not temperature. The main cause of deaths during fire is smoke poisoning, making up even to 80%. So smoke spreads quickly, significantly reduces visibility, increases panic. It makes evacuation very difficult. It makes the firefighting operation very difficult, if not impossible. And for this reason, Fire and Life Safety Code of Practice orders evacuation routes to be protected against smoke penetration in public buildings and in high-rise ones. To do this, we have to supply certain amount of air into the stairwell space to create overpressure in relation to the fire-affected story. The precision here is very important because the overpressure has to be high enough it has to be high enough to stop the flow of smoke if someone opened the door on the fire-affected story, but not too high, so this door can be actually opened. So pressurization system operation is a constant balancing between those two values. Pressurization is very simple under easy conditions. We just supply air until we reach a certain overpressure value. It is like that in isothermal conditions, so when outside and inside temperatures are equal. We in Europe call it spring, but here I called it winter, but you have to be aware that it can occur also during cold night. So the difference between temperature is important here. And why is that? Because the pressure is affected by many static and dynamic factors, but for tall buildings, it is the temperature that has the greatest influence. It creates something that is called a stack effect, and stack effect is a directed air movement due to a difference of air density. In hot climate, the direction is from the top to the bottom. So we have negative pressure at the top and positive pressure at the bottom. And why is it so important? Because if we pressurize the staircase, we move the pressure range, but we don't change the pressure spread. So the difference between top and the bottom pressure is still the same. The basic way of doing pressurization system is to use a constant flow fan with a pressure relief damper. It is usually located at the top of the building, but in hot climate with this reverse stag effect, it does nothing to mitigate stag effect. For this reason, to be intellectually fair, I have shown here example of pressure distribution of 90-meter high building with the system with the pressure relief damper on the bottom. And as we can see, depending on the season of the year, of the difference of temperature, straight line is winter and dashed line is summer, we have very different conditions on the, in the building. And what is the problem with this system? Pressure relief damper controls the pressure only in its surroundings, so it has very limited influence on the pressure in the entire building. And the second problem is that those systems are static, so they cannot respond to dynamically changing conditions in the staircase. The solution we developed and patented is very simple. We supply air to the under pressure zone and extract it in the opposite side of the staircase. But what is also very important, each fan is variable air volume, so it adjusts constantly to the changing condition inside the staircase. And thanks to that, we can obtain even pressure distribution in the entire height of the staircase, regardless the outside temperature. Thanks to that, we can ensure the best evacuation and firefighting conditions. And what with super high-rise buildings? Fire and Life Safety Code of Practice orders to divide staircases into sections not higher than 90 meters or to use pressurization system that counteract the stag effect. And why is it better to use the second option? It is for two reasons. Firstly, we can save the space that would have been used for second stair and passageways for commercial use. We can have profit from that. And the second reason is that separation of two staircases creates two pressure distribution, but as long as those spaces are actually separated. And during the evacuation of skyscraper with hundreds of evacuees, it won't be. As soon as the separation door opens, pressure tends to equalize. So we have one pressure distribution like in 180-meter high building. Again, when we pressurize it, we move the pressure range, but we don't this pressure spread. And pressure relief dampers don't solve the problem, because as we can see here in summer situation, if fire is on top floors, there is very big risk of incoming smoke to the staircase, while during winter, during cold night, people here will be trapped regardless where the fire is. And our system can keep the pressure precisely in the entire height of the staircase, and what is more, we don't have to split the staircase, so we can use the space, the spare space. And as I said before, we have to change the air volume depending on the conditions in the staircase, because someone opens, closes the door, this changes pressure inside. Usually a tracking controller is used for this, like PID. It is changing constantly the output value until input value, which is pressure measurement, meets the required value. It takes time, it is the first thing, but there is also a problem that the faster they work, the more unstable they become. So there is a risk of oscillation if the pressure is changed frequently. For this reason, we use predictive adaptive controller based on neural network that is for constant learning. So for from the first cycles, our device remembers in which event configuration what frequency it has reached. And thanks to that, in case of sudden pressure change, we know exactly what frequency we have to reach. Thanks to that, we have much faster response, and our system is oscillation resistant. What is more, thanks to that, we can have much bigger operation range. So it gives a lot of flexibility to designers because they can use the same unit, for example, for very small airtight space, but also for a very big staircase. There is no problem with that. 84% wider range. In our system, we use ring type topology, so we don't have to connect each device directly to the control panel, which is huge saving in the kilometers of fire-rated cables, and we can keep the communication in the case of loss of one line. But during fire, there a lot can happen. So what will happen if we lose communication with the second line, you may ask. And to be honest, not much, because our control panel is fire brigade access point. So they will lose the ability to check data or reset the system, but all of devices implement its algorithm by itself. So they will keep going during the fire. And to be sure that our system will be ready to the action, we made it to check itself every day. It opens shut-off damper, start the fan for a couple of seconds on few frequencies. Data is collected, recorded, and can be easily printed in the form of report. And thanks to that, we can eliminate very quickly any potential malfunction, and we can reduce the cost of maintenance, reduce the cost of periodic inspection. For complex system, we have a touchscreen panel for visualization of entire system, and if you want to eliminate the potential malfunction very quickly, we can put a remote access router in the building. Then, if there is a need, diagnose the system from our headquarters in Poland, fix it if it is software problem, or give an instruction how to do that if it is something else. So we in Europe don't build as high buildings as you here in the Emirates, but SMI has received a lot of experience and proven efficiency of its systems on dozens, if not hundreds, buildings in Poland and abroad, including the highest building in the European Union, Warsaw Tower. So we are going, we are ready for going higher. And coming back to our leading thoughts, safe evacuation is crucial as high-rise fires are occurring with increasing frequency, and human life is priceless. And for this reason, it is so important to use systems that can cope with stack effect and can respond fast and precisely to the changing situation in the staircase during the fire. And the modern fire protection systems, like modern cars, have to be equipped with solutions that not only protect their operation during the most demanding conditions, but also that allows for assessing their readiness during the standby mode. For this reason, we have fast-acting, the fastest oscillation-resistant predictive adaptive algorithm. We are ready for standalone operation if there are 2 breaks on the lines, and we've made our system to self-test every day. So that's it from my side. Thank you very much. Shukran, jazilan.